Good afternoon. Thank you so much for making time for my presentation today. I would have loved to be there in Berlin right now and attend the entire event. However, due to a personal circumstance, I'm unable to travel. I'd like to thank QtDevCon for allowing me to make this presentation on video. My name is Prashanth Udupa. I'm from Bengaluru, India. The first time I used Qt was a little more than 20 years ago for a university project. I've since been using Qt both personally and professionally. In March 2020, when the first pandemic lockdown broke, I started developing an open source desktop screenwriting app called Scrite. In a little more than 2 years, close to 7,500 people from all over the world have used Scrite, and almost a third of them are using it as their daily screenwriting software. I know of a few film studios here in India who have completely switched to Scrite for all of their screenwriting needs. I've been a widgets user for a very long time, but the unique thing about Scribe, for me at least, is that the entire UI of this app is built using QML. There's not a single widget in the entire app. This project has been a fantastic learning opportunity for me. I've had the opportunity of presenting two talks on the insights that I've gathered while developing Scribe at other conferences before. As the Scribe project began to grow, I started to notice certain issues while trying to use QML in a large desktop software. Certain parts of Scribe began to perform poorly as I loaded it with a lot of new features. And in certain places, I was really missing something like a graphics view. In today's presentation, I want to talk about some problems that I faced in Scribe and also showcase the solutions that I've had a chance to discover. Here are the four key points that I want to talk about in today's presentation. Let's get straight into it. Scribe makes use of model view to deliver its features. In the beginning, the models were small and the delegates were light and everything was great. However, as the project started to grow, models became bigger and more complex, and the delegates became heavier and more elaborate. And when that happened, views would become slow and the application would become unresponsive. Let me show you two specific places in Scribe where I encountered this issue. Here I've opened a screenplay that I wrote last year after reading a novel and adapting it as a 5-episode series. It's roughly 200 pages long and has close to 250 scenes. In Scrite, the screenplay object is implemented as a list model of scenes, which means each scene is an item in the screenplay model. Now this screenplay has close to 250 scenes. As such, a model with 250 items is not large, but the delegate we use to render the scenes from this model is rather large. Here's a scene delegate. Notice that it has a scene heading, a space for writing the scene number, a space for adding characters present in the scene, a space for tagging the scene with a structural beat, and then a space for writing the synopsis of the scene, and then finally a space for actually capturing the text of the scene itself. Now these are the visible ones. There are a bunch of invisible ones too. In fact, each delegate has about 150 objects and it takes time to instantiate these 150 objects. This is what I mean by a heavy delegate. Watch what happens when I scroll the text in this tab really fast. Notice how the app is struggling to scroll. This is because heavy delegates are being loaded even if they don't stay put on the screen for long because we're scrolling really fast. This is an example of not so large model but with heavy delegates. As a matter of fact, the model size wouldn't matter at all. If delegates are heavy, your views will be slow. Another example, let me switch to the structure tab. Notice how it's taking an excruciatingly long time to load. This is because we are loading heavy delegates in the form of index cards on the structure canvas. Each of these index cards contain many items. What you can see here is the item for showing the title of the index card, the synopsis of the index card, and down here we have a footer which shows the structural tag or the beat and also the characters in that particular scene. And then we have this icon here which we can use to drag and drop index cards on the timeline. Plus there's also this tab bar on some of the index cards which allows us to cycle through all of the index cards present in a stack. Now, this took a really long time to load, isn't it? How do we optimize this? I want to share two ideas. The first idea addresses the slow scrolling speed in Screenplay Editor, and it involves delaying the loading of delegates. The delegates we use in the Screenplay Editor are elaborate because they need to offer a lot of functionality. Now, instead of cutting down on functionality, we break apart the delegate into two parts. The first part is lightweight and it gets quickly loaded. This part of the delegate is loaded as soon as the delegate is instantiated by the view. A few hundred milliseconds later, we then load the more elaborate, heavier part of the delegate. Now, during this time, if the delegate scrolls out of the view, then the heavier part is never loaded. This results in a dramatic increase in performance within views. We're looking at the QML code for the Screenplay Editor. Now, within this, we have a list view. This list view shows scene editors for every scene that makes up the screenplay, and that makes up the Screenplay Editor. Now, in the delegate we assign to this list view, we make use of a loader whose active property is set to false. Now, the function of this loader is to load the actual scene editor itself. Now, by default, we don't even load the actual scene editor. We set the active value to false. So you just get a loader in the list view initially. As a part of the initialization process of the loader, we schedule a call to this load function 400 milliseconds after the loader itself is initialized. So that means for 400 milliseconds, nothing shows up. Now, while the active property is set to false, we make use of yet another loader to show a placeholder scene. Now, this placeholder scene is basically a rectangle that has the same color as the scene, and it shows the scene heading, and it shows something called as a placeholder scene image, which is just a blurred scene image like this. Let's take a look at the impact of all of these changes. Now, watch what happens when I rapidly scroll this list view. Can you see that the list view is showing the placeholder images while I'm scrolling? And you might also notice that the scrolling is much smoother than before. Now, as soon as I stop scrolling, the full-blown scene editor is shown in place. This has dramatically improved the scrolling performance of the Screenplay Editor. The second idea addresses the slow initialization speed in structured canvas, and it involves using something called LOD loader. List view creates only as many delegates as required, but a repeater creates one instance of the delegate for every row in the model. The structured canvas makes use of repeater to create an instance of index card delegate for every scene it gets from the screenplay model. Now, in a screenplay that has hundreds of scenes, it would mean creating hundreds of these heavy index card delegates, and naturally, the initialization time will suffer. But it so happens that we don't need all of this full-blown index card functionality every time. We only need it when the index card is selected, because that's when the user is editing and he'll make use of all of that elaborate functionality. At all other times, we can show a light version of the index card, and that's precisely what we do using LOD loader. The index card in the structured canvas makes use of something called as LOD loader to load the contents of the heading and the synopsis fields. LOD loader is simply a fancier loader. It picks between a low detail and high detail component depending on the value of the LOD property, which is low by default, but the moment it becomes high, an instance of the high detail component is created and then shown in place. The low detail component in both the heading and the synopsis fields is a basic text display item. This loads up very quickly. The high detail component, on the other hand, is a more elaborate item that is suitable for editing purposes. This can be heavy and therefore it will take time to load. Now, the value of the LOD property in both the LOD loaders is low for the most part, except when the index card is selected. This means that even if the structured canvas has 300 index cards, at best one of them will have its LOD property set to high, and therefore the performance of the structured canvas should dramatically improve. Let's take a look at the impact. Let me switch to the structure tab now. Look how fast the structure tab loaded. This is because all of the index cards are now only showing the low detail component. It's only the selected index card which is showing the high detail component. The performance of the structure canvas has dramatically improved because of this change. So that was about using large models with heavy delegates. Having used Qt widgets for a long time, I miss the text handling coolness of widgets in QML. But then again, it's not all bad in QML. You can absolutely do everything that you did in widgets, it's just that the approach is a little bit different. Now, for instance, as a desktop productivity software, Scrite must be as keyboard shortcut friendly as possible. And one of the most intuitive keyboard shortcuts is Tab and Back Tab. Now, Qt Quick Controls automatically handles tab and back tab focus switches. It moves the keyboard focus in the order in which they were created. But sometimes that's not enough. Of course, we can make use of key navigation attach property to get more control, but I find that to be a bit too cumbersome. Let me show you what I mean. Let me switch to the Structure tab in Scrite. Here we can create scenes, sequence them, arrange them to form a flow or shape so that we can comprehend our story better. Let me collapse the screenplay editor to one side and make more space for the structure canvas. We have an empty index card on the structure canvas. Let me capture the title of this scene here. I'll call this the first scene. Okay, good. Now I'm going to create another scene and I'll call this the second scene. Like this, I'm going to create the third scene and then the fourth scene. Now I'm going to change the color for each of these scenes so that we can tell them apart visually. Now we have 4 scenes. Let's take a look at the default tab sequence. I'm going to place the cursor on the synopsis area in the first index card and I'll hit on the tab button next. Notice that it is switching to the heading inside this index card and then it switches to the synopsis of the next index card, heading, synopsis, heading, synopsis, heading. It's kind of odd that the synopsis editor is receiving the tab focus first before the heading gets the tab focus, although in the code we create the heading item first and then the synopsis text area next. It's a little odd, but still manageable. Now let's say in my second draft, I want to mix up my story. I want to change the order in which these scenes roll out in my screenplay. Maybe I want to start with the climax first. And then whatever used to be the first scene, I want it to happen at the absolute end. So I've changed the order in which these scenes occur in my screenplay. Now let's see what happens to the tab sequence. Can you see after the fourth scene, the tab focus went to whatever used to be the first index card. Now when I hit on the tab key, the focus will go to this heading, and when I hit on tab key here, it will come to the synopsis area of the second index card because that's the sequence in which these index cards got created in the structure canvas. But that's not what I want. What I want is for the tab focus sequence to follow the logical order of index cards in my screenplay. Of course, I can make use of key navigation attach property and then explicitly assign tab and back tab items, but I find that to be a bit cumbersome. What if I wanted a tab sequence to get dynamically constructed based on a numerical index? And this numerical index can simply be attached to the index of the scene in the screenplay model. Now we can do this using a custom attach property. Let's take a look at the code now. In Scrite, we have a class called as tab sequence manager. This class manages the tab focus switch between a bunch of items. The actual items in this sequence are provided by tab sequence item instances, and we'll come back and take a look at this in just a bit. The tab sequence manager is a QObject subclass, and as you can see, we've used QML element macro in the class header, which means an instance of tab sequence manager can be created in QML code. The first property that we are seeing here is a property called enabled, and then we have another property called as wraparound. By default, this is false, but we can set it to true if we want the tab focus to wrap around once we reach the end of the tab sequence. Now, the tab sequence manager is actually an event filter. It installs itself as an event filter on the application object. Whenever a key press event is detected, And if the key press event is either the tab or the back tab key press, then the tab switching is actually handled by the tab sequence manager. Now, like I said before, the items in the tab sequence manager are tab sequence item instances. This is also a subclass of QObject, and we have used this macro called as QML attached, which means that instances of tab sequence item can only be created as an attached property to another item. This also has a bunch of properties. The enable property allows us to determine whether this particular tab sequence item should participate in the tab sequence or not. The manager property allows us to specify the manager to which this tab sequence item belongs. And then we have an integer sequence property. This allows us to determine the sequence in which this item is supposed to receive the tab focus. Now this was all C++ side of things. Let's take a look at the QML code. In the structured canvas QML code, we create an instance of the tab sequence manager, and then we add the heading field to the tab sequence manager by using the tab sequence item attached property. Similarly, we add the synopsis field to the tab sequence manager using the tab sequence item attached property. Notice how we are constructing the index sequence of the heading field by using the element index property. Now, element index corresponds to the integer position of a specific index card in the screenplay. If we resequence these index cards in the screenplay, then the value of element index will change, and that causes the value of sequence to change in the tab sequence item. The same thing is done for the synopsis field as well. Let's take a look at the impact of all of this in the UI. Once again, we have the 4 index cards on the canvas. I'm going to click here so that the synopsis field in the first index card gets the keyboard focus. Now I'm going to hit on the tab key and notice that the focus went to the heading of the second index card, synopsis of the second index card, and then third index card, and then fourth index card. Now when I hit the tab key, since we have configured a wraparound to true in the tab sequence manager, the focus is going to come back to the heading of the first index card. This is logical, isn't it? Let's resequence these index cards. I'm going to move the fourth scene to become the first scene, and then I'll move the erstwhile first scene to become the last scene in my screenplay. Now, what happens to the tab sequence? Still logical. By simply using a custom attached property, we are able to get a handle on how the tab sequence gets constructed in the application. Spell check. We have to make use of platform-specific third-party libraries to offer this feature. And not just that, it has to work well with TextEdit and TextArea QML items because that's what we use in Scrite to accept text. Let me first show you how the spell check feature works, and then we can take a look at the code. People use Scrite to write screenplays. In a way, it's a specialized text editor. And like most text editors, we bundle a spell checker along with the app. So if I write a statement with a lot of spelling mistakes like this, then you can notice Scrite highlights the misspelled words. I can right-click on these words and pick from a list of suggestions to correct the spelling mistake. Once the mistakes are corrected, the red highlights disappear. In Scrite, we make use of Sonnet from KDE to check for spelling mistakes. On Windows, we have developed a custom speller plugin for Sonnet that makes use of the COM interface iSpellChecker to orchestrate spell check. In Scrite, we have a class called a spellcheck service. We can supply any text to the text property of spellcheck service, and then this class will go ahead and check for spelling mistakes in that text. The text could contain a single word, a sentence, a paragraph, or even a couple of paragraphs. Whenever the spell check on the given text has started, it emits the started signal, and when it finishes, it emits the finished signal. The spell check service class performs spell check on a separate thread and is therefore asynchronous. Now, whenever the finished signal is emitted, we can call the misspelled fragments method to get a list of all the misspelled fragments within the supplied text. Now, each text fragment reports the start and end positions between which a spelling mistake was detected. We can call the suggestions method in this structure to get a list of all the spelling suggestions for the misspelled word in question. Now, whenever the value of the text property is set or the setText function is called, you'll notice that the doUpdate function is called. Now, doUpdate either schedules an update call or it makes a call to update right away. Now, within the update function, we clear all the currently known misspelled fragments, and then we construct a spell check service request data structure in which we store the text in question. And finally, we place a call to the check spellings function on a thread in this thread pool by making use of the Qt concurrent module. To the check spellings function, we pass the request that we just constructed as parameter. Now, the check spellings function accepts the request and then it breaks the text apart into word boundaries using Sonnet. And against each word, the is misspelled function within Sonnet speller is called to determine whether there is a spelling mistake or not. In case there is a spelling mistake, we capture that in a text fragment and compile all of these text fragments into a result. Now, like I said before, the call to check spellings happens in a separate thread. So we wait for the results to come in the future and then actually watch for that in a future watcher. Now, whenever this future watcher emits the finished signal, the spell check complete slot is called. Now, within the spell check complete, we actually accept the result and emit the finished signal. Now, this was just the spell check service. Now, let's look at the code which ties up the act of typing on the screenplay editor in the Scrite UI and the invocation of the spell check service to actually perform the spell check. We have a class called a scene element that represents a paragraph that the user is typing in the screenplay editor. Paragraphs can be of type action, character, dialogue, parenthetical, short, and transition. These are the types of paragraphs that any screenplay would have. Now, as each paragraph is typed, we set the value of the text that we type in the user interface into the text property of scene element. Now, within the setText method, which accepts the value of this text property, you'll notice that we are placing a call to the setText method on the spell check service. This is how we trigger the checking for spelling mistakes in the text that is typed by the user on the screenplay editor. Now, how do we highlight spelling mistakes from the misspelled text fragments on the user interface? This is done by making use of a subclass of QSyntax highlighter in the form of scene document binder. The highlight block method in scene document binder queries for misspelled fragments from the spell check service, and for each misspelled word, it applies a spelling error character format. This is how spelling mistakes get highlighted on the text area. Now, what about offering spelling suggestions in the right-click context menu? Now, whenever the user right-clicks on the text area in the UI, we capture that in a mouse area, and then if the word under the cursor was actually misspelled, we then pop up the spelling suggestions menu. Now, this menu actually makes use of a repeater to go over all of the spelling suggestions for the word under the cursor, and then it shows them in that menu. Now, once a suggestion is selected, we then replace the word under the cursor with the suggestion selected in the menu. This is how the entire spell check functionality is offered in Scrite. Together with Sonnet, QSyntax Highlighter, and Qt Concurrent, we are able to offer spell check feature on Windows, Linux, and macOS versions of the Scrite app. Sonnet handles all of the details when it comes to driving the actual spell check, except on Windows where we have written a custom plugin. Next, I want to talk about a feature that I took for granted in Qt widgets, but in QML, it took some work. One of the things I miss in QML is support for QCompleter in text field and text edit. In widgets, we can simply assign a completer to QLineEdit using the setCompleter method. Although we don't have something similar in QTextEdit, using QCompleter is not very difficult even in that scenario. In QML, support for QCompleter doesn't come out of the box, at least not that I know of. Like any word processor, Scrite also needs to show autocomplete pop-ups in a few places. Let me show you a demo. For instance, in the screenplay editor, we need a completer pop-up to show plausible character names whenever we switch to character paragraph. Similarly, we need autocomplete pop-ups to show up for shorts and transitions as well. Even while adding a character's presence in the scene, we need autocomplete pop-up to show up character names. The way we do this is by building a custom completion model class and showing the contents of this model in a pop-up item. Let's take a look at the code. So here's the completion model class. As you can see, it is inheriting from QAbstract list model. Now as a list model, it provides access to a filtered list of strings that is supplied to the strings property. Once a string is selected from the completion model, it emits this signal called as request completion. In response to the signal, the text editor items in QML can accept the string and then change the string under the cursor. In the screenplay editor, for example, we create an instance of the completion model. And then we supply the value of the strings property to be whatever is the autocomplete hints that is applicable at the current cursor position. Now when the request completion signal is emitted, we actually accept the completion suggestion. The contents of the completion model is shown in a pop-up, which in turn makes use of a list view to show the contents of the completion model. A mechanism similar to this is used in all the text edit areas within Scrite to offer auto-completion support. Scrite allows writers to generate reports and take an output of the entire screenplay itself. Internally, these documents are created using QtextDocument and then they're saved into a PDF file. But users wanted to preview these PDF files within the app before saving it to the disk. Scrite offers print preview for all the documents that can be exported to PDF. For example, here I extract character report for one of the characters in my story. The report is previewed within the app. We can zoom out to take a look at multiple pages at once. Now, Qt widgets users have the luxury of using Qt Print Preview widget to show a preview of these Qt text documents before they are printed. But how do we do this in QML? Previously, we were implementing the custom printer engine to capture contents of every page into a separate QPicture instance and then show that in the UI using a custom image provider plugin. However, in the recent builds of Scrite, we simply generate a PDF in a temporary folder and then show its contents using the image QML element. I can click on this button to generate a PDF of the entire screenplay, and that PDF is shown within this view here directly within the app. This works just as good as print preview, doesn't it? Here's another report. This shows key statistics in my entire screenplay. I can easily get bird's eye view of how all my episodes are paced in the screenplay. Rather than reinvent a brand new mechanism for print preview, we simply show the PDF itself using image QML elements. Let's take a look at this in the code now. In the Scrite project, we have developed a custom QML item called PDFView. This PDFView is basically an item. Within this item, we make use of Qt's built-in PDF document item to load the PDF file. And then we make use of table view to show all of the pages from this PDF document. The delegate associated with this table view makes use of image QML element. The source property of this image QML element is whatever is the source of the PDF document. And then we also specify current name as the page number that we want to display on the screen. So if a PDF document has 300 pages, then the table view creates as many image QML items as are visible on the screen, and each of these image QML items gets a separate page number. That's pretty much all we need to do to show a PDF document on the screen. And that's how we have print preview in Scrite. Next, I want to talk about displaying large text documents. While the document class used in Qt for both widgets and QML are one and the same, the way it's handled is different. Widgets paint only visible part of the document on the screen, but QML items like text edit and text area, they create scene graph nodes for every single glyph in the entire text document, even the ones that are not currently visible on the screen. Now, this can cause performance problems when we are trying to display a very large QText document. Now, for the most part, this does not affect Scrite because Scrite is a scene-centric editor. It creates a separate text area object for every scene in the screenplay. Now, a scene is usually a couple of paragraphs long. At best, it can be a few pages long, and that's not a problem. But when all of these scenes are put together, the screenplay becomes more than 100 pages long. Now, showing all of these 100 pages in one single text area is a bad idea. There is one place in Scrite where we need to show the entire screenplay text in one large scrollable view. One of the hidden features in Scrite is a tab called as Scrited. Here, we can synchronize film playback with the screenplay either to create learning material from films and their screenplays or to verify one's own film output. Let me open screenplay of a popular Kannada film and switch to the Scrited tab. On the left, we can notice the entire screenplay text presented in one large scroll. On the right, we can see items for specific scene and dialogue offsets in the film. Now, I'm going to drag and drop the film video on this tab. We can click on a scene to quickly scroll to the time offset in both the video and the screenplay text. By using a keyboard shortcut, I can negotiate the space between the screenplay scroll and the film video. I'm now going to check on this box that says auto scroll and hit the play button. Watch how the screenplay scrolls along with the film. The screenplay scroll shown below is rendered using a custom QtDevCon subclass called as text document item. Using text area for this purpose can be a rather bad idea because text area is not appropriate for showing large text documents. The text document item class is a subclass of QQuickItem. We mark it as a QML element so that we can create instances of this item from QML code. The document property allows us to set a QText document on this text document item. As soon as this property is set, the size of this item becomes as large as the document itself. Typically, screenplays tend to be several hundreds of pages long. So the size of this text document item tends to be much larger than the screen estate itself. Therefore, we need to show the text document item within a flickable item, and we specify the flickable item as another property to text document item. This allows us to compute the viewport that is currently visible to the user. We've implemented this item so that it calls the update viewport method whenever the flickable is scrolled even just a little bit. This way, we can determine which part of the entire document is currently visible to the user. Now, inside this update viewport method, we create an image so that we can capture the current viewport that needs to be shown to the user. And then we create a QPainter on this QImage. We query the text document layout from the document, and then we ask the text document layout to paint the contents of the current viewport into the image. And then finally, we supply this image to another item called as viewport item, which is placed within this text document item. Now, this viewport item is an instance of text document viewport item, which is actually a subclass of QQuickPainted item. The image is accepted in set viewport image, and this calls the update method, and this causes the paint function to get called. And when the paint function is called, we draw the image on the screen. This technique for showing a large text document is far more efficient than using text area or text edit. The screenplay format is rather rigid. There are only a few paragraph types, and the formatting options for these types are consistent across the entire document. Which is the reason why, even though screenplay is a rich text, we didn't have to provide a typical rich text editor. But recent user feedback has surfaced the need for a rich text editor, not just in the screenplay editor tab, but also in another place. Scrite has a notebook tab in which writers can capture their research. For example, we can go to story notes and add one or more notes to capture some research about the story. Scene notes can either be captured in the synopsis area here or as separate notes filed under the scene. Characters in the story get their own section in the notebook. Here, we can capture some metadata about the character. We can even assign a photo for the character in question. Now, this notebook tab can be merged into the structure tab so that research can be referred to while writing the screenplay. In addition to creating simple text notes for characters, we can also create elaborate form notes where we can capture research about characters in a very structured way. All of these notes are plain text notes. A few months ago, one of our users requested that they be able to capture notes in rich text so that it's easy to refer to these notes while writing the screenplay. Now, even though text area does display rich text, using it to provide a rich text editor, now that's some work. Initially, I took inspiration from a built-in example in Qt and set out to build a rich text editor in QML using text area and a custom C++ document handler class, which would apply formatting options like bold, italics, underline, etc. But soon I realized that building a robust text editor in QML, like the ones people are used to on the web and in other apps, is a really difficult task. That's when I felt that we are better off using a ready-made text editor like QuillJS, which is built using HTML and JavaScript, and integrate that in Scrite's QML UI using Web Engine View. The latest nightly builds now offer a rich text editor using this. Now I can format text notes using all of these options on the toolbar. This rich text area is built using QuillJS. Its Delta document object fits nicely with our own JSON-based document object. To exchange data between QML and HTML world in Web Engine View, we make use of Qt Web Channel. Let me quickly show you the code. In Scrite, we have a custom component called Rich Text Edit, which shows the rich text editor and the rich text content itself. Now, the rich text content is actually fetched from the content property of a note object. The note object is an instance of the Node C++ class. It's a subclass of QObject, and as you can see, it's a QML element that marks itself as uncreatable. Now, in this node class, we have a property called as content whose data type is QJSON value. Now, the rich text edit QML component is custom written in Scrite. It's basically an item which has a web engine view inside it, and this web engine view loads richtexteditor.html. Now, this is a simple HTML file, and inside this we make use of a div, and in this div we load the entire Quill rich text editor. Now, to the window.onLoad event, we assign a function in which we open a web channel for communication between the QML world and the HTML world. Now, the Scrite object is basically a Qt object. As you can see, we make use of the attached property webchannel.id to specify the name of this object or Scrite, and that's the reason why we are able to dereference Scrite from the HTML world. Now, this Qt object has a bunch of signals. Whenever these signals are emitted, the parameters from these signals get transported across to the HTML world. That's how we communicate between the QML and HTML worlds. For instance, there is a signal called as request content. This signal is emitted whenever the QML side wants to request for some brand new content to be shown in the rich text editor. Now, when this signal is emitted, we capture the signal in the HTML JavaScript world, and then we set the contents on the Quill. As the user types in the Quill rich text editor, a text change event is notified. We hook up a function to this text change event, and whenever we get this event, we capture the new content, and then we send that content to the QML side using this function called as content updated. Now, this content updated is a JavaScript function that's implemented in the Scrite Qt object, and that's how we get the content from the Quill.js side in HTML into the QML side. Now, this content is then cascaded across to the content property of the Node C++ class. And all of this orchestration provides the rich text editor functionality in Scrite. So these are some of the ways in which I handle gaps in text handling within the Scrite project. Next, I miss GraphicsView, I really do. It was my go-to module for building 2D interactive graphics. I loved how we could mix GraphicsView and QML when the first declarative module came out in Qt 4. But since Qt 5, it's no longer possible. Had I used the widgets toolkit for building Scrite, then I would have definitely used GraphicsView for the structure canvas tab. But I've already spoken about that in another talk. There is one more place in Scrite where I badly wanted to use GraphicsView, but I had to put together a workaround. I've already shown you a demo of the Notebook tab. This is where writers capture research about their story, about their scenes and characters. Now, in addition to capturing information in plain text and rich text notes, there is one other way in which information can be captured, specifically about characters. I'm going to head to the characters panel in this notebook, and I'll get this area where I can add characters that make up my story. So let's say I'm writing screenplay for the Friends film, and I'm going to create characters for each of the 6 key friends in the film. Now, as I create characters, you'll notice that a page gets created for each of these characters. Now, I'm going to head over to the page for Monica and then switch to the relationships tab. Now, let's say I want to capture relationships around Monica. I'm going to click on Monica and then hit on this plus icon. It's going to give me this dialog box, and in here I can say Monica is sister of Ross. She is a roommate of Rachel, and she is in love with Chandler. So I'm going to hit this create relationships button, and you'll notice that all of the relationships are neatly laid out in this graph here. I'm going to now double click on Ross, and you'll notice that the fact that Monica is Ross's sister is already captured. But let me go ahead and add a few more relationships around Ross. I'll say Ross is ex-husband of Rachel, and let's say we are writing the story of Friends sometime in season 5 or 6, and Ross is college friend of Chandler, and then I'm going to hit on the create relationships button, and you'll notice now the graph got updated and these relationships got included in the graph. So I'm going to place this over here so that it's easier on the eye, right? So we have this crisscross of relationships as it would be in any complex story. And now I'm going to go hit the double click on Chandler, and for Chandler I'll say Chandler is roommate of Joey, and then I'm going to double click on Joey and then say Joey is a very good friend of Phoebe. So I'm going to hit on this create relationships button. So I've gone ahead and created relationships around each of the 6 characters in my film, in my story. Now I'll head over to the characters panel in the notebook and then switch to the relationships tab here. Now this is going to show a sum total of all of the relationships that I've created. So we'll now be able to visualize who is related to who in a very simple, easy to comprehend graph. I can zoom in and zoom out. Now, if I wanted to implement this using the widgets toolkit, I would naturally use GraphicsView. But Scrite's UI is completely developed using QML, so GraphicsView is out of question. Instead, we can separate out data and presentation aspects of GraphicsView, keep all the data aspects in C++ models, and move all the presentation bits to QML. What we have in Scrite is a class called as character relationship graph. Now this class captures the data aspect in the form of nodes and edges. A node represents a character in the relationship graph, and the edge is basically the arrow that represents a relationship in the relationship graph. Now we are accessing nodes and edges as properties. They return a list model of node and edge objects. Now in the UI, we simply make use of repeaters to go over each of these nodes and edges, and we create different delegates for each of these nodes and edges. As with anything in QML, the character relationship graph feature had to be broken down into a model view problem. Now we do something similar to show multiple layers in the structure canvas. Information about the layers is captured in C++ models, and their visual representation is built using QML. I've already spoken about this in my previous presentations. In general, this is a good approach to building graphics view-like UIs using QML. Okay, enough of wishing for widgets-like features in QML. Let's talk about new opportunities that QML presents. Something that I really like in QML is animations. In Scrite, we make use of animations to really delight the user. We don't have to do big things. Like they say, small things make a lot of difference. I've already shown the use of animation in the Scrite tab. While playing back the film, the screenplay text scrolls along with it. Putting together this animation is very simple in QML, but you can imagine how useful this functionality would actually be for writers and filmmakers. In fact, a few studios have used this feature in Scrite to create script-to-screen videos like this and publish it on their social media pages. Let me open the Settings dialog box. Notice how the dialog box animates itself out from the menu item. I'm going to slow this process down a bit. Now when I click on the Settings menu item, the dialog box slowly reveals itself from the menu. When I click on this check mark here, the dialog box disappears into the same place from where it came. Not only does this look cool, but it also gives a subtle indication to the user as to where a dialog box came from. Like all word processors, Scrite is slow in a few places. I really wish I could work on a single QText document object from multiple threads. I wish I could export multiple pages of a PDF file at once. At some point, I really hope that I can build a document model that lets me work on several aspects of the Scrite document all at once. But until then, I have to make peace with the fact that Scrite will be slow in a few places. Now, rather than showing the UI as something frozen while the Scrite app is doing something, we show an animation to keep the user distracted. Now, because QML provides animators that allows us to run these animations on the rendered thread, we can afford to keep the main thread busy doing something while the user is presented some animation. We show some animation while trying to load a large screenplay from Scriptale, for example. We show animations while trying to switch tabs. By showing animations, we keep the user distracted and busy, and it also gives a sense that the application is handling itself well. Let me open Scriptale, our small library of screenplays hosted online. Now when I open a screenplay from here, Scrite actually downloads the content from our servers and displays it in the UI. During this process, we show an animated wait message. We even show this while switching tabs. It's a small thing, but gives the user a feeling that the application is handling itself well. So those were some of the ideas that I wanted to talk about in today's presentation. QML presents very interesting opportunities for developing applications on the desktop. After having developed desktop software for close to 18 years using widgets, I'm really enjoying my time developing desktop applications using QML. I hope you found my presentation useful and that it was worth your time. Thank you so much for listening.